sorry, I have some additional meetings just now, which, okay. Так. Okay. Okay, share screen. Okay, can you see my screen?
Yes.
Fine. So we will continue, and I will remind. So we are working with. We are working. With general relativity, and so what we did. Okay. Okay. We discussed the Einstein summation. So now you understand that if we have so if we have, for example, here, as in this example, we have even indexes, which, for example, we can meet twice or 4 times. It means that we have a summation. So we have this this sum. If we have, if we meet the index only once, it means that it tells us how many, for example, equations we have, as an example here. Now we will work with covariant and contravariant tensors, and we will discover the determination of this vector and tensors. And just a second, I need to finalize some things, and we will start. Okay, let's put the title of the lectures. Covariant, contravariant, vectors, tensors. So, and how many students today? 15. Okay. In the end, I will make a screenshot. Okay. So the point which we would like to discover this is to understand how we can transform, for example, coordinates and some object from one reference system to another reference system, from one coordinate system to another coordinate system. So and in principle we need to join not only just Descartes coordinates, but Cartesian coordinates, but also we need to consider any coordinate system, including coordinate system which we put on the curve space. So this is a point. In the first, we, for example, I can consider that this idea that we have one reference system. Let's call it with coordinates x. In principle, it can be xi, so x1, x2, x3. And schematically, I can draw it like this. So this is some coordinate system. And we go to another coordinate system, and it can be, for example, like this. For now, let's call it just for now, we will call it another. So if we have some, in the beginning, we will consider scalar, and after this, we go to the vector. So, and let's consider it not xi. Later, we will remark it like a prime and not prime reference system. It will be much more convenient for us. But for now, just to, because it's much more convenient to see different letters at the beginning, so I will put it xi. The first, and we want to understand how coordinates of some object in the space will change when we move from one reference system to another reference system. The first, let's consider scalar. So scalar will, for example, we have some function. Let's consider some function phi, which depends on coordinate x. Okay. And for example, this is some point, okay? And we want to consider, in principle, we can consider this phi doesn't depend on coordinate xi. So this is some scalar function. If we will move this scalar function, the scalar, it's not a not function, even so just a scalar. So it can be distribution of some value on some field. So we understand that with scalar nothing changed. So if it was some, for example, value of temperature in one reference system, we move on another reference system, it will be the same value of temperature. The value of the temperature, for example, doesn't change due to moving from one reference system to another reference system. So we the same for xi. So you can write that for scalar, nothing happened if we will move from one reference system to another reference system. Let's consider vector. So I will put here vector. And if we put here some coordinate lines, and for example, I will consider element of the length. So it sums the small length of the vector. I will put here dx vector. Okay, so which has a coordinate, which has a length along one axis. For example, dx1 here, dx2. If this is coordinate x1, coordinate axis x1, x2. In this case, if we will move in another reference system, we understand that the coordinate of the vector, for example, I will choose this. Now it will be xc1, xc2 in general case. And vector will, for example, like this. So it will be already different coordinates. dxc1, dxc2. And this vector dx vector. So what we can tell in advance? We understand that when we move vector from one reference system to another reference system, we will see, we understand that component of the vector will be changed. So if before, and this is which we are related with the components of the vector, but the length of this vector, which is some scalar value, it shouldn't be changed due to going from another reference system, from one reference system to another reference system. So, for example, if you have some ruler, okay, if you have some ruler, some solid body, doesn't matter. You have you choose one reference system, and you obtain some. You have some coordinates of the beginning and end of this body. But if you will move this body in another reference system, the size of the body will not change. For this case, the size of the ruler will be not changed. But of course, it will be changed coordinates. And for us, it's important to understand how these coordinates will be changed, but all time taken into account that the length of the vector will be not changed due to going from one reference system to another reference system. So this is such a kind of idea which we need to put, and we will find special mathematical objects which we will use, this is tensors, which exactly satisfy this this idea that changing of coordinates, but to keep the length of the vector as a constant. For the vector, we can now write that in one reference system we have, for example, vector dx with coordinate dx0. Let's put 1. We can, in principle, start to work already with the case of 4 vectors. Okay, doesn't matter. Dx1. So, and we can write it like a dx. Let's put a 10, for example. Okay. And here we can write, so if you consider 3-dimensional space, it will be from 1 to 3. If we consider 4-dimensional space, we put n from 0 to 3. So this is n equal 4 if we consider space and time. Usually 0 we put like a time, n equals 0, this is time, and 1 to 3, this is space. Okay. And in the second reference system, we will have dx vector, correspondingly 0 dx1, dx same. So we want to understand how, and we want to find the transformation of the component of the vector dxc in new reference system correspond to the previous reference system. To do this, we understand that we just need to use mathematical analysis formula. So we can write that dxc, and I will write for example, for put for 0 component. Okay, it doesn't matter for one component. Okay, equal. So what it will be? It will be dxc 0 dxm for dxm, just from mathematical analysis, okay? Because xc is a function of the x, of coordinate x. And otherwise, x also the function of coordinate xc. So, and just to write once, so I can open this summation. It means that this is dxc 0 by dxc 0 dx0 plus etc. Okay. For the second, I also need to write that this is the xc1, the xm, sorry, the xm, the xm. And the same for the xc2, the xc3. So this is relation between coordinates of the vector xc, the xc, sorry, with the coordinates through the coordinates of the vector dx. In general, we can write it that dxn equal dxn divided by dxm dxm. Oh, if we will put some notation, so let's call the vector A, and I will put index, so since the index n here and here, so this is upper index, I can write, I also will keep it as a upper index n. I will put here just to remind ourselves that this vector is related with the coordinate system, reference system xc. So just even put here notation that components. Okay, I can. It means that this is dxc0, dxc1, and etc. I also will put a notation that am in coordinate reference system x, this is the x0, the x1, etc. dxm, dxm, and here I will have am reference system x. Let's put it in frame. And we can give some definition. So you write, I just tell. So such a kind of vector called contravariant vector. Contravariant vector. Contravariant. Contravariant vector. And definition is the following. We will speak already, we will work in four-dimensional space, time, four-dimensional, yes, four-dimensional space, time. So, and we can give a notation, definition that contravariant for vector, contravariant for vector. This is a vector, or this is this is, let's call it like a set of four values. This is set of four values. So covariant for vector. Contravariant, sorry. Four values which transform from due to transformation of coordinates as differentials. Because you can see here that it's really transformed like differentials. As a differentials. To remember contravariant vectors, all time has the indexes which is above. So you can see here, okay, n and n from the left and from the right side. This is they're located. This is upper indexes. So, and when we speak about contravariant vector, it means, if I say contravariant vector A, it means that you need to put some index, exactly I or n, doesn't matter, but put it as the upper index. So this is a point. Later we will generalize this for the tensors. And vector, this is particular case of the tensor. So this is the next one. Let's do the following. Let's have some function which is a scalar function. So this function, if before as a number one we consider just one value which doesn't depend on the coordinates, now we consider scalar function, which is a, and for us it's interesting how this scalar function, which is in principle function of in one coordinate system, this is function of xn, how it will transform, how it will look like in reference system Xi. So if we can write that df by dxn equal And again, we are just using mathematical analysis. So we write df by dxm, dxm by dxm. So you can see here that what we wrote, we have an index n as a low index. Here, this is low index. Against index m, this is summation index here and here. So on the right side, we have the couple consider the df by dx. So again, we will put a notation. So let's call a with index now lower index n, and reference system xi, and n. Okay, so it means that this is the f by dx0, df by dx1. This. And also let's call a. Okay.
I'm so sorry.
Yes.
Sorry. Now we see, but before this time we doesn't see anything. Sorry.
Oh, of course, you need to tell me about this. But now, can you see?
Yes. No, exactly the last equation.
Strange. Internet looks like stable for now. So okay, what you didn't see before, starting again. Okay, I will repeat. So we just consider the derivation of the function f here. So if something happened, disappeared, sound, or you can't see my screen, please tell me. I can some repeat. So we consider the derivation of the scalar function f with a reference system xi here, the left side. And I just using mathematical analysis. So this is df by dxm, dxm by dxm by dxm. And I just wanted to tell that we will put some notation. So we call an here df by dxn with these components. Now I put I would like to call am. I can put n, doesn't matter. The reference system x. This is the f by xm. So again, it's understandable that this is df by dx0, df by dx1. Okay. In this case, I can rewrite this equation, this expression, the following way. So with these notations, it will be a, vector a. I put index below. Okay. I will remind myself that this is reference system xi equal. Now in the first I will write the xm by dxi n. So I used this term as a first term multiplier, and after this I need to put. You can follow for me if you and please check because what is important when we are working with tensors in principle general relativity, if you will lose some index, it's really can be crucial. For now, we just start, but later you will see that we will have many indexes, and it's very important to check everything. So if I will make some mistake or misprint, please, stupid mistake, please tell me. Okay, so I put here n and here x. So looks everything right. And now I will put it in frame. And this vector, which has an index, doesn't matter. I can put any index, but for definition, since I put here a or n, for this expression, of course, this is n. So this vector we call covariant vector. Covariant vector. And you need to remember that covariant vector, as soon as I write the vector with a lower index here, you need to immediately recognize that this is covariant vector. So definition, covariant for vector. I speak now about 4 vector, but in principle it can be 3 vector also, or 2 vector, or even if you are working in 10-dimensional space, if you would like, you say 10 vectors. But so we just since we are plan to working with general relativity, we will put definition for 4 vectors, which is in principle the same. You understand that if you will put n not from 0 to 3, but other number, you will have another dimension of space. So this is just general. Covariant for vector is a set of 4 values, a I, for example, or an. In this case, this is an, which transform, which during the transformation of coordinates, this vector transform as a derivation from scalar function, as a derivation from scalar function. This is what exactly we see here. So let's check now. So now we have 2 kind of vectors, covariant and contravariant. Later we will I will tell you about geometrical properties of this finally of this problem with existence of two vectors, because two kind of vectors, because when we are working in usually in flat space or in Cartesian reference system, we don't care about this. We are using just a transformation from one reference system to another, and we use just one components, one representation. So, but here we meet this one, and we understand why from geometrical point of view. But now I would like to check that really, if we will use such a kind of definition of the vector, covariant and contravariant, I can, I might say, I can create the object which is a scalar and which will not be changed due to transformation from one reference system to another reference system. So you remember that we discussed coordinates can, of course, will be changed, but for example, the size of the body, some important characteristics, the length of the vector should be the same. And let's check it now. Okay, I will. Let's consider the product. I will put covariant, and I say covariant, and you can see that I put index below. Vector reference system C on vector B, also reference system C, and so I put the same indexes. We understand that in this case it will be scalar because it means that we need to put, yes, A0, sorry, B0. Oh, that's stupid things. Okay, like this. Okay, it means that we need to put some AN, BN. Okay, A0, B0 plus A1, B1 plus blah blah blah. So we understand that it will be a scalar as a result. And we want to understand how this product, how it will be in reference system X. So now I will look on the transformation of the covariant vector. Okay, so and if I will look on this covariant vector here, so this is the dxm, dxcn. Okay, I write it here, dxm, dxcn on A. And also I want to mention that oh no, I can kill it. And I will remind it here. So this is right. Of course not. Okay. So I can see that I already have a mistake, especially that you could recognize it. I made a mistake. And this is good that this mistake I made, because now I can, this is not right. I need to put it here. The low index corresponding to this expression. And what is important, I would like to again to mention here, that the rule, mnemonic rule, such a way that if you have here low index, you need to have here also low index. So you need to control it as well as here. And of course, this is mistake too. Sorry, it should be here M, of course, because the summation under M. Okay, please check everything what I'm writing. If you have summed up, please tell me about this. Okay, so you can see here, and this is good that I write not right way. So you can see here that this M and this M, so this is index of summation. Okay, this low index here, and here you can see also lower index. So it's a denominator. Why is this N below in covariant vector? In the contravariant vector, you can see that this is index above upper index and this upper index. And otherwise, this index of summation. So now everything right. Should be very careful.
I think we now see previous page, which is
Previous
already
this
finished.
one. Ah, this one. So now we can
ah.
see that it's not right. So we need to write it like this. This should be M, of course. M. Okay. Now this is right. Agree? And we put here reference system X. And now we write for contravariant vector, because this is contravariant vector. So we write the transformation of contravariant vector. This is dx, sorry, dx. Since it's above, we can mnemonically remember that it should be in the first xi with n. Okay, d x. And now I will put index. In the first I will write this is a vector bx. And now I will put indexes. So I need to understand that here the m is a summation index. Doesn't matter. I can, instead of m, put any indexes k. What is important that it will be here. It should be here and here. Repeating we need to repeat the same index. So I can put here, doesn't matter, k. Here also, when we write for a contravariant component, we need to put the summation index. And summation index, we can't put the same as for covariant vector m. Index m. We need to put a different index. Let's put it, for example, k and k, because it's a summation for another vector. Okay, and this is bm. After this, I can write it. So just I will move the multiplier like this. dxn, dxn, dxk, okay. And after this, I will put m x b k x. Okay, so I just writing the same, but I decided to move for the multiplier after I am and before. What I can see from this expression, I can see that this summand, summand, not a sum, multiplier. So this is just a dxm by dxk. Okay. And we as we understand from all this summand, all this set, it will be alive only the case when m equal k. For example, if we will consider, if we will write it in x, y, z, okay, if we will 3 coordinates. So just we understand that dx by dx plus dx by dy plus dx by dz dz. So it's understandable that it will be 0. So we will have only finally the summand which d by dx or dy by dy or dz by dz. Okay, so we will have only the component, the derivation, which satisfies the conditions that m equal k. Others will disappear. In this case, we can write that it will be finally, and since m it will be life only m equal k. Of course, we need to write together with a b. We need instead to put k, we put m. So we can consider dxm by dxm. It doesn't matter to write it. I can finally to write am x b m x. So you can see, and we prove it, that really we choose the component of covariant and contravariant vector such a way, the definition of this vector such a way, say product of these vectors, covariant and contravariant, represents the scalar, creates a scalar, which really doesn't change when we move from one reference system to another reference system. So this is our main idea, one of the ideas. Okay, so you write the conclusion. Now we can make such a definition of another object, which we can call. We'll jump now. Go to definition of tensor. You can write now tensor. Maybe before it's better to explain. No, later. Okay, tensor. Doesn't matter. In principle, what we considered before, it was also tensor. So just you can mention that the vector, and later we will I will give a definition, general definition of the tensor, but in advance I say that the covariant and contravariant vector, in general case we call it as a tensor of the first rank. So AI, this is tensor, first rank. So, but tensor of the second rank. I want to create the object which has already the next rank, the second rank, and I can do it. Later we will consider example, and everything will be much more understandable. So I can do it in such a way. Let's consider the product AI BK. So in principle it can be proven. So and let's call it, for example, the T I K. So we have two indexes on the right, we have two indexes on the left. Again, we keep the upper indexes on the right side and corresponding on the left side. So I just, if we will remind the transformation of these vectors from one reference system to another, let's put it here C, here C, here C. So I can write, we can hear, so contravariant. It means that I need to, for AI, I write dx C I by dx, and let's put some indexes m, for example. Okay, and I will put here a m and x. I leave the place. For b k, I will write and you can see, by the way, that when we write contravariant transformation, we the xi, oops, sorry, the xi take this index, which you know, which you can see was before was belong to A. Okay, this is just for a mnemonic rule. After this, I write dx, and dx take index k, okay, from B, dx, and here I need to put some indexes, some index of summation. Let's put it n, b, n, x. And if I will call this T, M, N, I can immediately obtain a transformation of this object T equal. So now I will lose my energy to charge my AirPods. dxi, dxm, dxk, dxn, t. Now m go to the t, and n go to the t. So, and we can put it in frame. So we obtain the sum object, and we can prove that this object also, if we will consider the scalar value from this object, it will not change from one reference system to another reference system, the same way which we checked before. And this vector this object called as a contravariant tensor second rank. Also, we can construct, we can immediately to write, for example, the expression for covariant tensor of the second rank. So it means covariant, it means, so, and I understand that if I say covariant, it means that I need to put indexes as a lower indexes. And as soon as I say the second rank, it means that I have two indexes. So AK equal reference system C. And we can do the same. I will not repeat. I can just immediately understand how it can be organized. Okay, so look on the transformation here. I can see of covariant. So it will be dx by dx I. Here I put n dx by dx. And you can see again, xi take the indexes from the left part, from the t. K, I will put here m. And I put here m. It's better to write, since similar to formula above, m and n. So I can choose the summation index how I want. And here m, here n. And I will put this is in reference system X. Okay. So, and this is transformation. This is covariant tensor. The second rank. Of course, we also understand that it can be also the third possibility. So, in principle, we make a tensor which has a lower and upper index. So, and there is a kind of object also, and we will use it. No, how to say this. Okay, I'm not sure that I use right now. It's in English. Okay, call it mixed. Okay, mixed case. So mixed, it means that we mix the indexes. And I want to write like this. So what it means, one index I have here, another index I have here. And I can, so again, if we will remember that we can construct this tensor from two vectors, like a product of two vectors, this one, in this case, we understand how to organize it. I even don't need to write any proof, so I just need to understand. For the upper index, I need to write, this is contravariant index. So, and I write dxi, so xi take whole time index, and dx, here I put summation index. For contravariant, for covariant, it was for contravariant index, now for covariant index, I need to write otherwise dxi k, the x summation index n, and here I need to organize actually here n upper, so I put it here, m lower, I put it here. So, and this is okay, I need to write also coordinate reference system xi here. Okay, this is x. So, and this is definition of mixed case, the tensor which has a contravariant index. For example, we understand that also if we have if index I, let's put it index I 0, 1, 2, 3, so together 4. For the tensor of the second rank, we will have how many components? Tell me. how many components we will have. For example, for the vector is a tensor of the first rank. We have
so we need tensor of second rank, or
yes, for the second.
Okay, so 16 components.
Of course,
we
16
will have.
components. Yes, 4 multiply and 4, so 16 together. So you already can feel that this is much more cumbersome evaluation calculations which we need to do where we are working with the tensors. Again, the beauty of general relativity is such a way that finally we will discover that and the Einstein equation, this is equation which you're using the tensor of the second rank. But before to reach it, we will reach the tensor of the fourth rank. But what is important and beauty of general relativity, which I hope finally you will see, is that the symmetry which we will use will allow us to obtain, as we, for example, applied for cosmology, for the models of the universe, we will see that finally we will obtain just a few equations. At the end will be even 2 equations. So, but to feel it and to see it, we need to continue to walk with this not incredibly long way, but some way to see this beauty. Okay, this was like philosophical. Okay, now there is of course a different operation with the tensors. We will consider maybe a little bit later. For now, I want to discover some geometrical property, geometrical idea, or this kind of covariant, contravariant tensor. So the geometrical explanation is the following. In principle, this is the appearing of these two kinds of the tensor from geometrical point of view. It is related to the fact that in general we are working in any space, including curve space. And when we have a curve space, so if we have a flat space, it's understandable that we, in principle, can choose Cartesian reference system, the Carter reference system. So, and our axis of the reference system is, like this. So this is rectangle. How call it? The angle between this axis 90 degrees. So everything understandable. But as soon as you consider a more general case, for example, the curve space, you can have much more like this coordinate axis. I consider on the example of 2-dimensional space for now, because it's much more convenient. So in this case, this is origin of the reference system. In this case, if you have a vector A, oops, let's put it here. Okay. We need to understand which rule we can choose to find the components of this vector. So for the case of this, the Carter reference system, Cartesian reference system, everything understandable. We just put perpendicular, and this is will be so x. Let's put 1, and this is x2. Okay, so everything can. But here, in this case, we can consider we can find determine the component of the vector by 2 cases. The first way, this is consideration using the basis. So it means that we can put like this, you know, to put line parallel to the coordinate axis. Let's call it x with index 1, x with index 2. So this is expansion in by the basis, using the basis, because of course we need to put as here some basis vectors. Let's call it E1 here, E2. Here we also need to put some basis vectors. From another side, we can do it in another case. So like consider like a projections on coordinate axis. Projection on coordinate axis, the second way. So the first, this is basis. The second, projections on coordinate axis. We can put perpendicular. Okay, let's call it x1. So just put different index, and this is x2. x2. And in this representation, we can use the same definition that if we have coordinates, the set of coordinates, indexes, upper indexes xi, these coordinates we call contravariant coordinates. And this one covariant coordinates. Okay, so it, and if we have, again, we will go to Cartesian reference system. Okay, in this case, contravariant coordinate and covariant coordinates are the same when this angle between axes became 90 degrees. So the point when we, from geometrical, this is, we can put geometrical explanation, okay, geometrical explanation. So just this is just a feel why we have these two kind vectors. So this is a result that in general space can be not obviously flat, and we can't if this is not a flat but curve. In the simple case, we can just consider the sphere, the surface of the sphere. And in this case, as we understand, we already not use the Cartesian reference system. It's not convenient. So we are using the spherical reference system. Or like if you have a cylinder, we have a cylindrical reference system. So, and we will consider these examples later. So I have 5 minutes. Okay, 5 minutes. I'm not sure that I can start something else. 6 minutes. Let's stop on this. And if you have some question, please ask me. No? Okay, in the next lecture, we will consider the metric tensor, which is crucial for maybe in this 5 minutes I can just to show you, since we speak why it's so important that this color will be not changed also. So if we will remind the special relativity, I will write Minkowski space-time. So I can write, if you remember, ds square. So this is element of the interval equal c square dt square minus dx, so dy dz. Okay, this is special relativity, and this is Minkowski space. What I now wrote, this is the square of the interval for the case of the flat space, because we remember when we speak about special relativity, we are working only with a special relativity theory called the special, exactly using this word special. And an exam I also will ask about this, because special, it means that this theory apply for the special reference system, which are inertial reference system. Okay, so the motion is with a constant velocity. But the general relativity, and why we call this general relativity, this is for the general case, including also non-inertial reference system. And after this, again, we need to remember, but why general? So this is not inertial system. Why we speak about non-inertial system? Because due to equivalence principle, we put as an equivalence to the non-inertial reference system, we put the gravity. And now you can immediately remind this Gedanken experiment of Einstein for the solid, for the rotating disk. It brings us to the curve space and time, and consider gravity as a curvature of the space-time. And again, you need to remember that we speak about space and time. So, because as soon as we start to work with relative theory, we already consider continuum together with space and time. Okay? Here I write the metric, we call it like metric. Later we will work with this, with a metric tensor, and for the special relativity case, for the Minkowski space, as we say, okay, Minkowski space. So, but what for us is important? So you can see, I put it, and you can recognize here Cartesian reference system, dx, dy, dz. This is exactly the summand which is related with the time. But what for us is important, that the ds, the interval between two events, is the same, doesn't depend from the transformation from one reference system to another reference system. So this is for us is like a scalar, which should be not changed. Okay, so on the next lecture, we will consider the metric tensor. We will consider also the operation with the tensors, which will be very important for the next step. This is covariant derivation. If you have some question, please ask. If not, I will make now screenshot of you. Please wait. How all of you understand that, so you have some additional messengers, how you understand about, about this Telegram account, to join to this Telegram account of Cosmology?
Can repeat?
No, we create some Telegram chat to you know, to put the link of the lectures and so on, which was made in Telegram Messenger. How students know about this? Because I didn't distribute this, or you have some additional chat.
Yes, we have some chat, and they are put a link for chat of cosmology.
Super, perfect. It's very good. Now I check screen. Okay, thank you. And we will see you on Friday.
Thank you, and goodbye.